welcome everyone to another edition of What Physicists Do, in which we continue the theme of speakers I personally know. In this case, we're very lucky to have Dr. Sojuy Roy, staff scientist from the Advanced Light Source at Lawrence Berkeley National Laboratory. The focus of his research is the properties of magnetic materials, particularly materials that emerge from having one type of material make contact with a different type of material. Emergent properties of the boundary between layers of magnetic materials. Sojuy Roy got his Master's of Science in India at I'm afraid, a university I can't pronounce the name of. Then he moved over to the United States where he got his MS and PhD from Southern Illinois University in Carbondale, where he studied engineering physics. He spent a few years as a postdoc at UC San Diego working with the legendary Sojuy Sinha, at least legendary in magnetic materials and X-ray diffraction work. After that, he worked as a staff scientist at the Stanford Synchrotron radiation light source before deciding to move across the bay to the Advanced Light Source, where he is now the group leader of X-ray diffraction, the X-ray diffraction group leader. And he's also now an adjunct at the University of California at Santa Cruz. And that he'll be talking about, among other things, magnetic skyrmions, and especially how radiation from synchrotron X-ray sources can be used to examine their properties. So let's all give a hand to Dr. Sojuy Roy.
Good afternoon, everyone. As this slide says, my name is Sojuy Roy from the Lawrence Berkeley National Lab. Before I start, let me first thank the department for giving me this opportunity to come and talk to you about our work, about the work that my group does. And also it's thanks to James for hosting me all day. So as the title says, I will be talking about shining light. These are special type of light that hopefully you will see throughout the talk. That these are light but not really ordinary light. A little bit, it has a kick to it. So before I start, let's start with a pop quiz. Anybody wants to guess? Any undergrad wants to guess what it is? Yeah.
Is it a skyrmion?
No. No, it has got to do with light. So light with a bright and dark. Does that reckon anything?
Diffraction.
Right, exactly. So this is actually a diffraction of an X-ray beam going through a pinhole. So that gives rise to this dark, bright circular fringes, so-called the airy fringes. So that would be these guys. But it is slightly complicated than that. This also has a modulation on the circle of these dots, right? These dark, bright here. So this is actually a hologram of a big pinhole with a small pinhole. So you can take your cell phone and you can take a photograph of it, and then you can import that into MATLAB and just write one line FFT of this, and it will give you the real space feature. So just to show you that I'm not just saying for the heck of it, it is not a fake news but a real news. This is what it is. So this was the structure. So this is the so-called this is my object, the big hole. And these two are the reference holes. So you know a hologram needs a reference hole. So it goes and references out, and then that is the data I would get. So the beam will fall on this thing, that is the data, and then you can take a Fourier transform, and then you can immediately see that these two, can you see this little one? So that's the big hole and the small hole. Now why there are four? Okay, so anytime you took an intensity, it's a field and its complex conjugate. So this is the real and that's the complex conjugate. Okay, so then you basically get what it is from a hologram. It turns out, at least my experience is that light is a powerful probe. There are very few things that light cannot probe. It's kind of amazing. So it can probe, of course, structures. That's the diffraction, field of diffraction. It can probe spin. I will show that. It can probe electron through resonant X-rays. It can probe conductivity, which is an opposite of resistivity, through visible laser. So light can probe actually many different things. But for this type of experiment that I'm going to show to you, we need to go to this place called Synchrotron, which is nothing but, it's actually a big machine that generates out X-rays. So it's in some ways, it's a very big X-ray generating machine. So what it has is that there is a small accelerator inside. I mean, there are a lot of engineering details, but as a physicist, we tend to forget about those details. So there's a big there's a small electron gun, it generates out an electron here, and then it will be accelerated very close to the speed of light. Of course, not to the speed of light, that will be ridiculous, but kind of, at the ALS where I am at, it generates like 99.8 or some 9 to the speed of light. And then once it does that, it is injected into this big red colored ring. And what it does is that a relativistic electron going through a magnet, do you know what it does when an electron goes through a magnet? Exactly, it feels the force. So it basically bends, and anything it's bending, it has to give out its energy, right? It's a relativistic electron, so it will give out its energy, and the energy will be photons coming out in the tangential direction. So that's why all these so-called lines that you see they are X-ray lines, and they are all tangential to these magnets. And those, depending on how much energetic these electrons in this red ring are, these X-ray beams will have that kind of energy. So literally a synchrotron has nothing but these so-called magnets where an electron goes and it slowly bends out from its position, and in the tangential direction the radiation comes out. If it is really an X-ray generating machine, why do we need to have a synchrotron? Why cannot we do in the lab? Because lab also has a lab diffractometer. Many of you do work at the diffractometer, right? That's because it's a place where you can tune the energy of the X-rays, and I will show you why is that very, very important. So in a synchrotron, you can tune the energy of the X-rays, and the other big thing is that it's intense. It's very, very intense. It's impossible to get that in the lab. So for example, at the ALS where I am at the advanced light source, which is a soft X-ray photon source, so you see the sun is here, and the ALS, the undulator which produces the beam, is about 9 orders of magnitude intense than the sun. And that's what does the trick. That's what we need in order to do little sophisticated experiments, okay? So they can be hard X-rays. For example, copper K alpha radiation. Anybody knows what's the energy for copper K alpha? Electron comes and hits in a copper anode, and out comes the beam. Anyone? It's 8 kilo electron volts. Compared to that, soft X-rays are pretty soft. So it goes only till 2 kilo electron volts. And the beauty of that is that for hard X-ray, you can study structure and lattice. If you remember your books, then the Kittel has this thing, the diffraction, X-ray diffraction, the lattice. So they need hard X-rays. But the soft X-rays are very, very sensitive to electronic and magnetic features. And I will use those X-rays to study electronic and magnetic features of a material that gives rise to this topological feature called skyrmions. Yeah.
Can I want to follow that. And the hard X-ray, when you're talking about structure and lattice, it's on the scale of the intermolecular sort of bonds, and you're sensing those. And when you're saying soft X-ray, magnetic structure and electronic structure, you're talking about being able to kind of see where the electrons are residing around the atom. Are we thinking of this as peering into the model of the atom, or electronic structure intermolecularly?
It's actually a very good question. So the basic, I will show later on, I have a slide. But this way, so if we just go simply with the Bragg's law, then 2D sine theta is lambda. So in that case, the D space that we can probe is say 5-6 angstrom possible with a hard X-ray. But soft X-rays, the wavelength is something like 15-20 angstrom. So in that case, we can't probe the lattice anymore. But it just turns out that the magnetic features, a lot of the time, the domains and skyrmions and other magnetic features or electronic features like ferroelectric domains, they are 100 to 200 nanometer. And then this 2 nanometer wavelength beam from soft X-ray becomes very, very important. And then you can also do similar Bragg law to study those features. And then I will tell you a little bit that how we get this electronic and magnetic sensitivity, and you will see that. I think that's a very good question. So you can see that in order to do this work, I cannot do by myself because it's impossible to do by oneself. Anybody who's going to Synchrotron to do this work, these are called user facilities. We can't do that. So I have the great fortune to work with some fantastic people over the years. So the main person here I'm going to show a lot of work is by James, and he did a lot of very, very good work. And then at Oregon I worked with Spencer. He's the graduate student, and Ben is still the faculty. I've worked with some samples from Tokura's group in Tokyo University, and in Urbana-Champaign with Karine Damen and her postdoc Karina. And Arnab Singh visited me for 3 months from Saha Institute in Calcutta in India, and I'm going to show some of his work. I'm going to show some work from Matt Langner. He was a joint postdoc with Bob Schoenlein and me. And some work by Sergio Montoya of these. The blue ones are the one who are the postdocs, and the main guys, and a lot of them have moved on to do big and better things. So James have become faculty here. Arnav is graduating very soon. Matt has gone on to work in the Silicon Valley, and Sergio has gone on to work at the Pacific National Warfare Lab. All right. So now, before we study this, before we put on this big work on synchrotron, as you will see that it is not an easy job, and it actually takes a lot of people, as I'm showing in the beginning. Why do we really study magnetism? Why do we have to? I mean, there is no reason for us to study, but is there really a way that we can think that, okay, it is useful or not? So I'm going to show you that it is indeed an interesting thing. So this is 2005, okay? Everybody is eager, and they're looking somewhere. They are looking in a direction where the name is Vatican, and the name of the Pope is about to be announced. So everybody is very eager that who's the Pope. And there's, of all this image, there's this one person with, it seems to me like a cell phone that has a data plan, probably those days. And then you fast forward few years, this is the same thing, Vatican, the name of the Pope is about to be announced again, and I don't have to tell you the difference, right? Now everybody has that cell phone. There's this another one that I like. So this is in 1950s, IBM machine, the big computer which probably took half of this room, and this is a micro drive. And going further down, I don't have to tell what are all these, all of us have this, and we are getting very mad that how come things are not fast enough. But this fastness from this smallness from there to here or there to there, and this thing that everybody has a data phone has not happened in vacuum. We really need to understand this. That has happened because people like faculties here, people like faculties everywhere, and graduate students like you and undergrads like you have studied physics and have studied very hard in technology and have put in effort to understand that how a magnetic thin film, when put in contact with another magnetic thin film, behave at the interface, and what properties those interfaces have, and how those properties can be taken and put into a technology. And that's I think is the basic essence of doing magnetic research. It is a field which is fundamental in physics, because without quantum mechanics you cannot explain magnetism, but at the same time it has a huge application area. I mean, you cannot think of modern electronics and electrical industry without magnets. So that's, I think, is the beauty, at least for me, of studying magnetism. But we are actually hitting the limit. If you read, so there's a very nice article on Economist, that how the Moore's law is coming in. So initially everything is becoming smaller and smaller and cheaper, right? But that cannot continue for infinity. That doesn't make any sense. So it will hit a limit, this so-called Moore's law, where you cannot make it further small, or you cannot make further cheap, or faster even. So the question is what to do about it. And that's where these two new things come. One is this tremendous development of synthesis technology. So now you can make heterostructures, thin films of whatever way you want to make. For example, if you are growing lanthanum oxide and strontium titanate, you can terminate a layer as you feel like. Say you want to grow 2.5 unit cell, you can do that. You can make a metallic thin films of whatever thickness or however composition, you probably can do that. And that is giving rise to many, many new and interesting properties. And then the other development is this development of topological features. So topological insulator, and this is another topological entity like quantum spin liquid and things like that, which have all these esoteric properties. And finally, today's topic, which is this topic of skyrmion that I'm going to talk about. So these are all topological features. So in parallel to this is another development that is happening, and the goal really is to think about it, understand their properties, their physics, and how they can be used for technology. So let's spend one slide on what is skyrmion. So I saw in the web that James did give a talk on skyrmion, so probably he talks a little bit about it. So there may be some repetition, I apologize, but hopefully you'll find it interesting. So what are skyrmions? These are stable particle like spin texture. So what does it mean? So let's think with me, you guys think with me about the parameter space. So it's a parameter, so ours is real space, right? X, Y, and Z going up. So think of the spin space. You are in the spin space where Sx, Sy, and Sz are the 3 coordinate axes, and there a soccer ball like that has formed, of spin soccer ball. So the spins are going outwards in the direction. If you take that spin space structure and project it on a real space. I saw a poster in the corridor of a very nice topological poster where they show how donut becomes a cup and things like that. There's a poster. I think that's an exact thing, right? So if you take a soccer ball and you project it out onto the real space, then that's what it looks like. Do you see how the spins are going and forming a knot and coming back out? So it turns out that if there is a knot in something, you cannot unknot it. Have you ever noticed it in a garden hose pipe? If the pipe is straight, it's one thing, but if it forms a knot, you just cannot pull a knot. You have to go back, unknot the thing, and then you can have to pull it out. So that when a knot forms, it's a special texture, a topological texture that you just cannot get rid of. So whenever we are talking of skyrmions, it's this kind of topological texture, like this guy has a kink here, or those two, these are the kinks of in the spin. And how they are characterized? They are characterized by an associated winding number, that how many times they wound around. So on the spin space, the sphere, this guy went in and came back again to its same position. So it has a winding number of 1. That's the main thing. It clearly is not a ferromagnet, because ferromagnet is a straight thing. There is no winding business in ferromagnet. It's also not a density wave. So I don't know, maybe this is a bit too much, but a density wave is something that happens in a solid, like a magnon is a density wave, which is like a wave going through the wave of spins. Spins are aligned so that as if a wave is going through the solid. So it's also not a spin density wave. The way to think about it is just very simple, that let's say there is a ferromagnetic exchange that's causing all the spins to align, and there is a what I call as a kicking interaction, an interaction that causes the spin to form an angle with respect to each other. And one of those type of kicking spins is this Zaloshinsky-Moria interaction, the so-called DM interaction. So when these two you add up, they compete with each other, and outcome, this is our drawing that, this is actually a calculation that Matt Langner did. So this is our own calculation that came out of these two terms, and you can form a skyrmion. So you can see that how the spins, just like that, is up, then down at the center, forming a kink and coming back. So at infinity, the spins are all aligned, and at the center, the spins are forming downwards. They are very good for technology because, as I said, once you form a, my battery is dead, sorry. Once you form a kink, you cannot unkink a kink. So you can see that it can easily flow. We can easily flow through the defect, and there are many.
I suggest we go old school.
Oh,
with
very
the
nice.
pointer,
Thank
yeah.
you. I was just looking for something. And then there are other ideas how to use skyrmions. So one of the big things is that they can be flown through the material with very low amount of current. And then Wu has done some interesting X-ray work. There are some interesting ideas of how to use it for a magnetic memory and things like that. So with that introduction, the talk is that I am going to study those skyrmions, and I'm going to show that how X-rays are very good for it. I'm going to quickly go over how we discovered this. Skyrmion. We did not discover skyrmion. What we did discover is that resonant X-rays are sensitive to skyrmions. And then I'm going to show that how we can use it in thin film. And then finally, I'm going to show that how a slightly different idea of using X-ray beam and how we can generate out vortex X-ray beams using some interesting nanostructures. All right. So this is the historical perspective. Basically, I don't want to go through in details, but in 1960, a high-energy physicist discovered skyrmions. He was trying to solve the problem of interaction of two pions, and he found that these are kind of spin textures that appear, and then it was dead in condensed matter physics for a long time, till in mid-70s. Two Russians, they figured out some kind of an interesting spin texture that happens in 2D magnetic films, but they did not realize in skyrmion. But what happened is that it came back in 2009, and I'm going to show that how it came back. But before that, I have to tell you that it came back in manganese silicide. And just to tell you what manganese silicide is, also a pretty old material. And it has a cubic structure, and people did a lot of neutron scattering on this kind of texture, and this is something that is an overall view. But for you to just focus on the fact that there are all these different phases, there is this one phase, it's called phase A. And that's because the authors, they did the neutron diffraction, they solved the structure, and they did see that this phase is different than all of this other phase. But they quite could not understand what that phase is. So they started talking about it like a phase. A phase that they know is different, but they really can't figure out exactly what it is. So they started talking about a phase, and it was like this for a very long time, till in modern times, Christian Fleiderer and his guys, Muhlbauer, they came forward and they did this interesting neutron scattering. This is again the phase diagram. So this is the paramagnet, helical, conical, and this is the so-called A phase. And within the A phase, this is the interesting, most interesting part of this thing. This is now a really famous paper. So the manganese silicide is a cubic structure, just like a cube. So it has X, Y, and Z, and it's a helical structure, meaning that in the X direction there is a spin helix going, in the Y direction a spin helix is going, and the Z direction a spin helix is going, right? So each helix will give rise to 2 diffraction spots. So they see 6 diffraction spots due to the helix, 3 helices, and then when they apply a field, the 6 diffraction spots remain 6, but only they are rotated a little bit. And that's very, very bizarre. I mean, why would something just rotate out? So then some theorists came and explained that this can happen when a spin crystal forms, and such a spin crystal will look like this with a hexagonal pattern with a spin swirling like a vortex spin. And that is exactly a definition of skyrmion. So that was the modern day reinvention, rediscovery.
I mean, this is fascinating. We've heard now a couple of talks this semester, and not all the students will have been to all of them. But if I may, you were saying there was this discussion, saying that these structures can exist. This was not really followed up on, and that slide is, let's look at interesting materials, probe them with a neutron beam, and find out, because that's with a known spin that you put in, and when it comes out, you're getting some idea of the spins or the orientations of the atoms inside that material. And there was a whole pattern where it did, the A phase, this is what I just learned this semester, the A phase is this thing that wasn't behaving like anyone expected, and it's going to be, wait a second, it's this thing from this paper.
And I think you brought a very important point. So the manganese silicide people are studying since 1960, right? Nobody could find this thing. That's because everybody was applying field in this direction. You see the crystal, this is the sample. And the beam comes in and they scatter, and everybody was applying field in this direction. Muhlbauer and Fleiderer are the only ones who figured that, wait a minute, if it's a skyrmion, then it should happen in the plane perpendicular to the film. So why don't we apply a field in the beam direction so that the skyrmions form in this plane? And that changed it. Nobody did that. It's these simple things that you do. You think a little bit harder than everyone else, and then you get the new result. So thanks for bringing that up. I think this is very important. Why did they get and others didn't? And that's the reason. Because everyone was applying field here and not in that direction. And then Tokura came and he did this fantastic, his guys actually, they did this very good LTEM, so transmission electron microscope in the Lorentz mode, where you can map out the B field, the induction field of the spin texture of the material. And they did show that there is this helical phase, so it's going like this, staircase of spins, and then that morphs into skyrmion, hexagonal lattice, and then this is one of the zoomed in image of the lattice, and then they did all kinds of phase diagram and everything else and topological Hall effect. But basically at this point it was set that, okay, you have a new type of spin textures which looks like a skyrmion, which behaves like a skyrmion, and it's topological. So once you form, it's not easy to destroy them. And then there are many reviews. I have listed some of them. They are by no means comprehensive, but they are very representative. If you want, you can go and search. Their sizes can be varied from 1 micron to 1 nanometer, so a big range of sizes are available. And there is a huge research field in the magnetism. So what I'm going to show is that how did we come into this business. So we have been studying manganese silicide. So the moment manganese silicide came in, MNSI, we noticed it and we started researching for 2.5 years. We looked at it. We were utter failure. We couldn't find anything, and for a technical reason that if you want I can tell you later on, and it was not us but no one else in the world also could find. And then we found this paper, copper oxide, selenium oxide, which is a multiferroic, meaning that if you apply an electric field, its magnetic property changes. If you apply a magnetic field, its electrical property changes. So that's why it's a multiferroic. The orders are coupled. It's a ferroic material. And the big thing to C here is the lattice constant of 8.5 angstrom. And this comes to your point that we are using soft X-rays. Okay, so that's wavelength is very large for us. For light wavelength is very large. So we could now access the lattice Bragg peak of this material. But before even that, just to show you, this is not our work, from Tokura's work in science, that he does find that there are helical states and there are skyrmion states. So very similar to the manganese silicide. And this caught our attention because we know now that for this material we can access the Bragg peak, the structural Bragg peak 001, which we could not do for manganese silicide, whose lattice parameter is only 8 angstrom. So we could not, 5 angstrom, sorry. So we could not access that. So how would we study these things? As I said, we will use X-ray scattering. So just a slide on that. This is just a photo I took from the web, but all of you probably has taken some of these photos of sun setting here and there. The thing to here see is that this line here. Can anyone say why this line is blurry? Why is it blurry? When do you think it will become non-blurry? Yeah.
It's because it's like the light is coming towards you, but it's coming like in every direction, so it bounces off the water and then hits your lens.
Well, it is clearly bounces over water, but why is it blurry though? Do you think if I put a mirror, it will be blurry? Like a plain mirror?
It's because the water's not like perfectly smooth.
Ah, fantastic. That's what it is. So the water is not smooth, it has ripples. So ripples are roughness on a flat surface. If it was a flat, you will just see a sharp spot, right? But because it's ripple, it does. So what you can take the data and you can analyze out, and you can figure out the height of the ripples and the correlation length of the ripples. So these X-rays are very good in figuring out these kind of in-plane features of a sample, right? So my technique is an X-ray technique. So let's go over in 2 slides, the X-ray technique. So let's say there's a sample, a beam comes in at an angle of alpha and is going at an angle of beta out. Let's say there is a structure that exists at a length scale d. So in the reciprocal space, it will be 2 pi over d. As simple as that. And then you can work out this formula for alpha equals to beta. The qz, which is one of the direction, is 4 pi over lambda sine of alpha, which is just plain Bragg's law. Basically what it means is that if you know d, you know what angle the beam has to come in, what angle the detector has to be, and then you can see a spot of diffraction from the material, right, for a given length scale d. So then you can go through any of your quantum mechanics book, undergraduate books, and you can easily see that in the so-called Born approximation, which is a weak scattering, this signal at a reciprocal space is related to the Fourier transform of the electron density. So what does that mean? The simplest case of that, if you want I can show you, I don't want to just go over it, is Thomson scattering, which is the scattering factor F is directly proportional to the Z number of an element. That's why aluminum doesn't scatter, that's why gold scatters more, that's why you can see bones and you cannot see tissues. There's a simple reason, just the Z number. Signal happens in Fourier space, which is the reciprocal space where everything is inverse of the real space, which is this interesting thing of diffraction. So if you see a dot in diffraction, that's a 3-dimensional structure. So when you do in your lab classes a diffraction, you see a small dot, it's a 3-dimensional crystal. And if it's a 1-dimensional, it will be a constant light, right? But the funny thing here is that, look, the important thing is that there is no magnetism anywhere. It's all Z number. To get to magnetic sensitivity, we have to get to this kind of complicated resonant X-ray scattering where the beam has to be tuned in a way, that's where the synchrotron comes in back again. Remember I said there's a tunability, such the energy of the beam is such that it makes a transition from a P core level to outer D shell and then comes back. And when that happens, suddenly the scattering factor becomes this horribly complicated. I'm not expecting any one of you to go over it. Just to think that there is now a magnetic term and now you get sensitivity of nickel and cobalt, which are magnetic materials. So basically, ultimately what we have to do, we have to come with an incident beam that is resonantly coupling to one of the element, and then we should be able to see. So let's do that on our copper selenide sample. This is back again as a sample. It will be aligned so that the 001 is into the detector. We will apply a magnetic field, and then that's how the skyrmions will form. And if you are an X-ray, let's imagine that you are X-ray, you are looking at this material, then for you, you will see this spin swirls in the Bragg plane with a reciprocal lattice distance of tau. Let's do that experiment. Let's get the crystal, let's align it, and let's see what do we see. So that's exactly what we see. So this is the 001 Bragg peak. And with respect to that Bragg peak, remember, the Bragg peak is in this direction, the z direction. So it gives a Bragg peak, and within the Bragg peak, at a distance tau, it sees the spots due to the swirl. And this is the first demonstration that X-rays can see skyrmion. So this is what Matt did, and we then drew out the phase, and this is this famous A phase back again. This exact textbook, and then we did some other things just to show that we have done a diligent job and things like that. So that's what got us into skyrmion, and since then we have been doing this is a few years back. Yeah.
Doctor, you brought up, I thought, a really interesting component where I was thinking kind of new about X-rays and medical imaging, and I just kind of closed the loop if I could.
Sure.
You said that we get density amount, but we also are having the Z or the heaviness of the atoms change and make that. And then you went through, hey, we're going to use the synchrotron to tune, and we're going to tune to know specific materials. So instead of just knowing that there's material there, we can tune it to look for the cobalt or the nickel. And I don't want to take you away from your thought, but
no, sure.
Is there in medical imaging where you could take, I think medical imaging seems like a blunt instrument compared to this, where it's a scalpel and you know something very specific. I wonder if there's work where the people are trying to do this kind of imaging in vivo, in tissue, to know
not that I am aware of, and part of the reason is that everything has a pro and con. So the beauty of hard X-ray is that it doesn't get absorbed, but soft X-ray, the way resonance works in detail, is that it's the Kramer's chronic of the absorption. So there has to be a huge absorption to get an enhanced scattering.
So much more dangerous.
So when soft X-ray sits in your tissue, it will absorb tremendously. Having said that, soft X-rays have found tremendous use in polymer industry, where people are using carbon edge to understand the sigma bond, the pi bond. In battery, so people in the ring, they have teamed up with big companies like Black & Decker and things. They come, bring their samples, and they're tuning in and figuring out in lithium iron phosphate, how are all these elements working up when it's really the battery is working. So there are those other applications of soft X-rays coming out. But directly medical imaging, the one that you were asking, I think it has a danger of getting too much of dose directly.
But the battery companies come to Lawrence Berkeley Lab to try out new materials because this can study the structure.
They can study the element-specific business. Yeah, okay. The electronic structure. It's okay. Then I have to speed up a little bit. And then we started getting into what believe James talked, a little bit of iron gadolinium. I believe he has said that these are the thin film materials that also gives rise to from a striped phase all the way to other phases, and we studied that. So now we have this kind of sample, the beam comes in, now tuned to, anybody paying attention? What is the element we should tune into? For copper selenide, we tuned into copper because it is the magnetic element. In iron gadolinium, where should we tune into? Which one is magnetic, you guess? Anybody? Iron gadolinium. Anything?
Iron.
Yeah, thank you. So you tune into the iron L3 edge, 707 EV, and you will see a diffraction spot. That's what James did, putting a lot of effort, I would think. And he got this fantastic magnetic diffraction pattern as if something is heavily aligned. So these are the domains aligned in the thin film sample. And then as he is changing field, he is getting nice structures and finally getting this beautiful hexagonal structure. And by now, hexagonal structure, aha moment for us, because is this a skyrmion? Because we know that hexagonal structure can resemble a skyrmion. And then we went on to do a lot of other things. James calculated out the structure factor of the material, and he figured out indeed it is one of them. And then we went to Ben McMorran at the University of Oregon, and he used LTEM and just to show that how the thins are evolving. So this is a stripe phase he starts from, and then he's changing the magnetic field, and you will see how things evolve, okay? And you'll see slowly changing and morphing and breaking and becoming more better stripes, then some forks, and then right now they are forming the skyrmions and they are becoming saturated. So this is an LTEM that he is taking as a function of field, And then these are some of the snapshots that we did. And from there, I'm just not going fast here because I know that you have heard it before. What James did is that he figured out a very nice phase diagram of this material as a function of magnetic field and a temperature, and you can see all these different types of interesting phases that appear in this iron gadolinium film. So now the question is that if I take that phase diagram that I just said, I can make a schematic out of it. So these are the disordered stripes. So what is happening, I should say before here, sorry, I probably should say. So this is a highly aligned stripe structure. That's why they are giving diffraction spots, right? Anything highly aligned give very strong spots, as I said. And then they are giving rise to a skyrmion. So question is that when James measured the phase diagram, he found that there are highly aligned stripes. There are a little bit of disordered stripes, like noodle type, labyrinth. And then there is a skyrmions and uniform magnetization. So we can now make this kind of schematic. So there is a disordered stripe, ordered stripes, and skyrmion. And then the question is, what is happening to this point, which is very similar to a triple point, right? If you think, you know what's a triple point, like water is a triple point. So similarly, what's happening to this triple point, and that's what we would like to know. That what is happening as we are approaching from all direction to this point, it seems to me that it could be a special type of point. And question is that a special type of point? So that's what we would like to know. And in order to do that, we have to think that fluctuations are very important. You know why fluctuations are very important? Because think about it, as you are near the phase point, as you are near the critical point, the material doesn't know what to do. So they are going between this energy well, that energy well, and they are continuously hopping and fluctuating because they really do, both energetics are same, so they don't know, and they fluctuate. And out of this fluctuation appears the new phase. They suddenly choose one phase to go in. And that's where the fluctuations are important. So just to show you that is it really the case, let's think of a very simple experiment. Let's say you have a container and then you have a sphere. And all you are doing, you are dropping a sphere, one after another, into the container, right? So if you do that, probably that's what will happen. Some balls will fall here, some balls will fall there. It looks like pretty disordered. If you look a plan view from the, if you look a plan view from the top, this will look like that. And then if you fluctuate, basically you shake the container a little bit, right? It is likely that for the correct size of the spheres and correct shape of the container, these are my two boundary conditions. If you're in physics, you know that physics is all about boundary conditions. You write an equation, you put boundary conditions, and you try to solve it. So it's exactly similar, right? So for the correct size of the sphere and correct shape of the container, if the shape of the container is a triangle, clearly this doesn't work anymore. So for those two conditions, this guy will look like that, right? It will be suddenly an ordered structure. So now if symmetry is a signature of a phase, which it is, then this is phase A and that is phase B. So see, this simple experiment can tell you that just a fluctuation, take something and you are shaking how it is going from a disordered phase to an ordered phase. So it is that important, actually, indeed, fluctuation. And if you go to StatMech book in graduate school, you will see there is a whole chapter towards the end which just basically deals with fluctuation. So in order to study fluctuation with light, I will introduce one more difficult concept, which is the concept of coherence. So this is an incoherent light, right? These lights are pretty incoherent lights, meaning that the phase and the amplitude of the light are all mixed up. So in order to get a coherent light, what you do, you put a small pinhole into the path of the light. So, and a monochromator, sorry, that's what this guy is. So we put a monochromator. So we take away, let's say it's a white light, we take away all the light and let red light pass. And then I will put a small pinhole to make it a point source. So that will create a wavelet at a long distance. It will look like a plane wave, and plane wave by definition is a coherent source, right? So that's what I'm going to do. So I'm going to use a coherent light. Now why I need to use a coherent light? Because I'm studying fluctuation, right? So what it does is that a coherent light measures correlation. Other lights cannot measure correlation. You remember why we want to measure correlation? Because we are fluctuating, right? In order to know the difference between this and this, you see the number of spheres have remained same. So if you are diffracting, the total number of scatterers have remained same. So there is no change of intensity. But there has to be some change. The light has to see difference between this and that. How do you think you make the difference between this and that? Why do you think this is different than that? Anybody? what makes you think that this and this are not same? To me seems like it's very same because they are same number of scatterers, same container. Okay, let's see.
Well, I mean, the arrangement and over there, if I have one, I
Yes.
don't know where the next one will be.
Exactly, it's the arrangement. It's the arrangement. So your eye is seeing, and this is a different arrangement. So the light, the X-ray beam, of course it cannot think like you guys, it's not smart enough. But it has to see this difference, and that's what coherence does. So how does it do? So let's say this is a labyrinth domain pattern. So if I take a regular light and diffract off, it will give a ring of scattering, so-called Debye-Scherrer cone, right? And then if I put a coherent beam, then it will suddenly split up into this so-called speckle pattern. You know what's a speckle pattern? A speckle pattern is the light interacts and goes out. When it goes out, it's self-interfering with itself because it's coherent. So if you put a laser, I don't have the laser, sorry, the battery went away. But you see a laser light on the wall, you will see it's always like this. It's not a flat surface because it's coherent beam. As it traverses, it interacts with the dust and re-interferes with itself. So it is never a flat surface, it has a structure. So this is also the same thing. So the overall envelope of the intensity remains same, but now it is modulated by the structure. And this structure inside the modulation is exact footprint of the way the things are on the surface. So for example, if I go back here, the intensities will be same, but one will have a different speckle pattern than the other one. So just by noting the speckle pattern, you will be able to see if the two things are different or not. So we use that, and then let's go back and to study the domain jumps. I'm going to show in iron gadolinium. So this is our two structure that James found out, right? This was the stripe, and this is the skyrmion, and then we use a coherent X-rays on it. Same thing will just diffract, and suddenly you see that this nice smooth structure breaks into small modulations from the domain. And same thing happens with the skyrmion. Now they have all kinds of modulation. Meaning these two textures are different in the sample surface, and every time I change anything, these speckles will also change. Right? One of the other way to understand speckle is very simple way. If you have done a double slit experiment, right? You take a double slit, a light goes in, there's a big envelope, and within that envelope there is a small up and down, up and down, up and down. Now let's think of the double slits are moving continuously. What happens? The overall envelope remains same because the double slit thicknesses are not changing, but their positions are changing. So the in-between fringes, they are continuously moving. That's exactly what it is, okay? So we did that. So what are we going to do? Sorry. Oops. Oh, one of my main diagram went away. Sorry. This is bad. What I was going to do is that I am going to take a very series of speckle pattern and I am going to correlate one with the other one and see if they are exactly same or not. If they are same, then their correlation coefficient remains same. If they are different, then the correlation coefficient jumps, right? So when I do that, I have a very nice diagram. I don't know why is it not showing up here, but that's exactly what I see. So as we are changing the field, so you see these sudden jumps are happening, as if the domains are suddenly going through a big jump as I'm changing the field. And the moment it enters into the skyrmion phase, all the jumps go away. This is kind of obvious, right? Because if you think about it, if you are forming a one-dimensional line in front of a movie, for example, somebody comes and pushes you out, it's easy to get pushed. But if you're holding hands and forming a circle, you can distort yourself, but not easy to break the chain of the holding hands, right? It's exactly the same thing. So we found that there are some interesting jumps as we are changing the magnetic field. The domains are going over some jumps. Those are the space fluctuations, so to speak. And then, as I said, that if it is going through a critical point, then the fluctuation will increase, right? Near the boiling point, or as you are approaching the boiling point of water, you will see from the bottom of the container, the bubbles are coming slowly, and then they fill the whole container with bubbles. And you don't know which bubble is coming where. It's exactly the same thing. So that means if we plot the size of the fluctuation, which is analogous to the size of the bubble and their appearance, they should peak as we are approaching the phase transition. So that's what we plot here, and we show indeed that's what is happening. It is really peaking up near the so-called that point, the 3 points, right? So it is indeed a critical point, and this is important in physics for StatMech. when you will, some of you will go and do better physics than me, then you will see that that's an interesting point. It's a critical point and it comes with its own physical properties. So we found out that that little point is indeed a critical point. And then we worked with Karine Dahmen at Urbana, and then she gives us this nice theoretical background, and ultimately what it is that those, we can plot out a histogram of those jumps, and they will scale with temperature, with a critical temperature, and scale with field, with a critical field. And we did that. I don't want to go over this. This is basically, if you want, interested, I can show you. This is so-called the collapse of the scaling, meaning that they all belong to one class, and from there we got the slope of the curve and the cutoff. You know, what does that mean? So these are the curves that we get from the histogram, and they have a slope. You can fit a slope, like a straight line slope, and they have a cutoff. It's rounding off. So those are the two important parameters that appear in StatMech. From there, you can guess about the phase, about the uniqueness of a phase. So we did that, and what we showed is that the slope of the skyrmion and the stripe phase are same, meaning that although there are no jumps in the skyrmion, from a slope point of view, the distribution of the jumps, they may be small, but the distribution is same. Whereas the cutoff, which is related to the correlation length, they are very, very different. That means that the stripes, at least together, they have a lesser coherence, phase coherence than the skyrmion themselves. So that was a nice study. This is done mostly by Arnab and a lot of help from James. So that's where we are with our skyrmion. In the remaining 4 minutes, I'm just going to finish up the vortex beam. So this is where we are today with our skyrmions. I'm now just going to show you an interesting thing, very changing topic, because I'm also getting very interested in the so-called X-ray photonics business. So we know that light has a spin angular momentum, right? So circularly plus light, circularly polarized minus light, and they have a spin angular momentum of plus minus h cut. And they are used to study so-called X-ray magnetic circular dichroism, which probably you don't have to know right now, but just hear from me that they are very important for that. But it turns out that the beam can also have orbital angular momentum. So this is a spin angular momentum, which is intrinsic, but it turns out that the beam can have orbital angular momentum, and that's heavily used in optical communication, and you will see that why they are heavily used. And I will tell you the connection between this and our skyrmion work, okay? So back in 1992, Allen has this, actually by now is a famous paper, where he showed that if you have a Gaussian beam, so a beam which is a Gaussian, which you can explain by a Gaussian, has this kind of plane. If you take a slice of the beam, then this is what you will see, right? A beam propagating from that direction to this direction. But you can actually make a Gaussian beam into Gauss-Laguerre beam, meaning that it will suddenly have this e to the power I ml 5 phase factor in the beam, and it will look, the phase will be a helical phase, and that's what it will look like. So if you put the beam on a plane, it will just look like a donut beam. Yeah.
Are all of those movies, so the middle one, I'm seeing the polarization just...
No, it's not the polarization, it's the phase. It's the phase factor that's moving. The polarization is still linear. The light is, the E vector is doing this way. The phase factor is doing a helical pitch as it is going along the K direction. That's actually the beauty of it. So with polarization, you can study magnetism, ferroelectricity, and many other structure itself you can do. This is a special case where the phase is going through a helical direction. So phase is doing this as it is going along the beam direction. So, see, this is the connection. So from here to here, what is the change you are seeing, everyone? What is the change you are seeing? It's in your poster, the topological poster. Whoever is paying attention to that poster. It is changing its topology. The beam, see, you can't get this beam from that beam. You cannot punch a hole in a pancake and think that that's a donut continuously. You cannot continuously make a pancake into a donut unless you are punching a hole through it. So you are discontinuously changing something. So that's what this guy. So in photon terms, we went through a photon phase transition. Very interesting if you just think about it, right? And in this phase transition, there is no temperature. There is no temperature, right? There is no temperature change. It's just a change. So how will that happen? So people thought about it. There are many small, there are So this is how it will happen. So for example, it can happen through a fork material. If material has a fork dislocation, then it can happen. It can happen through a spiral faceplate or through a nanostructure that is revolving. You see all the time you're getting a donut beam. And even in LCLS, Hemsing has this interesting idea of using a seeded laser, X-ray laser, and getting an OM light. So we got very interested, and I saw Ben's paper. By that time, we were already working with him about our skyrmion and LTEM, and I saw this paper by him. So we got very excited. So in order to do that, what we have to do, we have to make this lattice. Do you see the lattice? And do you see the fork here? Everybody see the fork here? It's a dislocation of one dislocation, right? So the beam will come, hit here, the center beam, and then on the two opposite side, you will have LF plus 1, LF minus 1, LF plus 2, LF minus 2. So these are the beams that are orbital angular momentum carrying beam. By the way, why do you think these are the opposite L's? Anybody? Why do you think these are the opposite L's?
I mean, you can't see it from the bottom row, but the top rows are showing them spinning in the opposite directions. Is that what you're saying?
Could be that way, that you are seeing the figure. That's what you are saying. But if there is a symmetric argument to it, which is more elegant, which is that this beam doesn't have an orbital angular momentum. So the total beam has to have a net orbital angular momentum of 0. So these guys have to all add up and become 0. That's why they are opposite. Okay, so we thought of that. So this is one of his Ben's work. So James patched up with Spencer, who actually unfortunately left the program. Very sad after this nice work. So this is our setup. The beam will come, some baffles in the beam to clean up, then we have the sample, and then we have the CCD detector. So this is our nanostructure that Spencer made. So you can see a one fork here. Neglect this bar, this is just for the strength of the material. And then James did the scattering, and then you can scatter off, and immediately you can see this nice orbital angular momentum. This is the first time anybody generated out X-ray orbital angular momentum beam, meaning that on this direction, on the exit direction of this nanostructure here, the X-ray beams are carrying orbital angular momentum. And then we can create a lot more. We have created all the way to 30 H bar, and it's limited to 30 because after that there is no intensity left. That's the problem. We can do a little bit more with it. We can cross two fork gratings in perpendicular direction, just like here. So you can take two fork. So this fork will give diffraction in this pattern, this direction. That fork will give diffraction in that pattern. And in the cross term, you will see all kinds of interesting things. And that's exactly what the predictions are, and that's exactly the experiments are. So you can see in this direction it's 2, in that direction it's 1, because there are two forks in this direction, one fork in that direction, and this is added up, that's the subtracted. So what I call is you can even try to do mathematics, and not only that, you can now create so many different types of beam at one go. So you came with a Gaussian beam, and then on the output you can get all kinds of beam with all kinds of OAM. And then you can mix and match, and you can do many different, various different interesting things. And the final thing is this, I like it, because this is an interference pattern coming out of it from this guy. Anybody wants to take a guess how much is the OM number? What is the orbital angular momentum number? It relies on your counting skill. You can do it. So this has an O of 5 plus and 5 minus. So plus 5 and plus minus 5 minus are going and they're interacting and giving rise to this very beautiful interference pattern onto the detector. And I thought it was fantastic, and not only me, Nature Photonics thought that's fantastic because they put it on their web page, and I just took a photo of that. It was very good. So now that we have created the beam, question is that what do we do with it? What do we do with such a beam? So laser, as I said, in laser community or the visible light community, the O beams are very good for communication and optical cryptography and things like that. I personally believe that X-rays are not that good for those purposes because there is already laser, which is much cheaper. I mean, who wants to build a synchrotron to do optical communication with this? So, but I feel that there are other applications for it. For example, one can do nano spectroscopy. You can make it specially sensitive to orbitals. You can do a topology enhanced scattering. For example, let's say a skyrmion coming into a no beam, and the moment it's matching up, it's going to show some special signature. I don't know, but I predict that's what will happen. And then finally, we can think of elastic and inelastic scattering with this flower petal, because anytime it will reflect off, the whole beam will go a phase rotation, some angle phi. But if it is inelastic scattering, it will either lose contrast or not lose contrast. So those things can happen. And finally, I think this gives a handle also for the first time of creating a spin orbit coupled X-ray beam, where the beam has a spin angular momentum and orbital angular momentum, and they can be coupled. So that's almost like a quantum photon states in the X-ray regime that we can think of creating. So that's about it. So I hope that you are kind of convinced, if not fully convinced, that X-ray scattering, resonant X-ray scattering and coherent X-ray scattering are very powerful tool. We have used it to study skyrmions. We showed that how we found skyrmions using these type of materials. We show some interesting characterization of these skyrmions. We have done some other work at LCLS, which I did not show because I just thought that it will need way more introductions. But we can do that, so we can use to measure fluctuation. We can understand the critical point. We can understand how is it behaving in space in sense of fluctuation as well as in time. And finally, I showed you how we have generated out soft X-ray vortex beams. And then going forward, we are doing a lot more with it. And maybe sometime if you're interested, just show up into the lab and I'll show you what we are doing with such a beam. With that, I'm always looking forward to your collaboration. If you're interested, please talk with me. As I was telling some of your professors, the DOE where I am at, so DOE is our funding agent, the Department of Energy, they do have a lot of program for undergraduates to come up and work there in summer and other times. If you want, I can forward you those information. It's a very wonderful place to come and work. And this is the lab, this is the light source. For those who are interested, this is a historical dome coming out of Lawrence's time. So this in the LBL, you will see always a logo of this dome, and that's because it was built in the time of Lawrence. And the joke is that apparently, I don't know true or false, but in one of the faculty meetings, they were arguing. He wanted a bigger space. Somebody told him, "Hey, there's a hill. Why don't you go up there?" And he said, "That's true. The hill is there. I should go up there." And he went to those days of DOE. I don't know what is that department would be. And he said that I need to build this big thing, Synchrotron there. Can I get space? And they said, "Yeah, go ahead." And that's how the dome got built on the top of the hill. With that, thank you very much and appreciate your hearing me.
As we're just approaching 5, those who are here for extra credit are free to depart quietly as they can, and then we'll take questions from the general audience.